In this video, we will discuss the connection of traditional machine learning models with shallow neural networks. In the previous lectures, we have discussed that neural networks are optimization-based machine learning models. But we also know that many classical machine learning models use continuous optimization. Some examples of these models are, for example, SVMs, linear regression, logistic regression. That's among the supervised models. And among the unsupervised models, we have singular value decomposition, also matrix factorization of incomplete matrices for recommender systems. That is also a continuous optimization model. What is interesting is that all of these models can be represented as special cases of shallow neural networks. So there is a natural continuum between machine learning and deep learning models, wherein many of the traditional machine learning models can be represented as shallow neural networks with a small number of units and a few layers. And that is one of the reasons that these classical machine learning models reach their learning capacity early, because they have few parameters and they only have a few nodes. But when we have more data, we can add more computational units to increase the complexity of the model and improve performance. So this is one of the reasons why deep learning methods often have better accuracy when the sizes of the data sets are large. So what is the advantage of deep learning over traditional machine learning? So exploring the connections between neural networks and traditional machine learning is useful because it exposes the cases in which deep learning has an advantage. So there are several things that you can do with a simple neural model that you get in classical machine learning. So for example, if you have a shallow neural network which represents an SVM or a logistic regression classifier, it tells you that by creating a more complex model that combines many such similar computational units, you can add learning capacity to the model. Secondly, you can control the structure of the architecture of the neural network to incorporate domain-specific insights. So for example, many successful classes of neural networks, such as recurrent neural networks and convolutional neural networks, have been developed with an understanding of domain-specific insights in the cases where they are used. Then there are other cases where by making minor changes to the architecture of a model, you can actually build very interesting machine learning models. So one example is that, for example, you have a neural model for linear matrix factorization. And one of the things that we'll show in later lectures is that by adding a nonlinear layer at the end of one of these models, as the final layer of one of these models, you can get a more complicated nonlinear matrix factorization model. So you can get, for example, logistic matrix factorization or multinomial matrix factorization. In fact, one of the popular feature engineering methods for text, it's called word-to-vec, which we will discuss in a later lecture, is a classic example of logistic or multinomial matrix factorization. So let us explore the relationship between the perceptron and the support vector machine. In the lecture on the perceptron, I had discussed what the relationship was between these two models. So let us revisit it briefly. So here I have shown two figures. The left one shows the architecture for the perceptron, and the right one shows the architecture for a linear support vector machine. Now, what you'll notice immediately is that the two architectures are absolutely identical. There is no difference between the two. The only difference between the two is in the nature of the loss function. So, in the case of the perceptron criterion, and in the case of the hinge loss for the support vector machine, they are only different by a shifting unit of 1. So you can see that the formula for the loss in the SVM, an additional unit of 1 has been added to one of the terms on the right hand side. So, so essentially what this means is that the perceptron criterion is a very minor variation of the hinge loss. And in fact, the update, as we discussed in a previous lecture, the update for the perceptron is identical to the support vector machine, the gradient descent update. The only difference is the condition in which you make the update. So in the case of the perceptron, you update the weight vector when the instance that is being classified has an incorrect classification. In the case of the support vector machine, you not only update for misclassified instances, but you also update for instances that are marginally correct. So essentially, this is the notion of the margin that is used in the SVM. So let's look at a pictorial representation of the perceptron criterion and the hinge loss. So here on the x-axis, I have shown the dot product of the weight vector and the training instance for a positive class training instance. So as you can see, and on the y-axis you have the loss. So as you can see, the perceptron criterion incurs a loss only in the case where it's misclassified, where the value of the dot product of W and X is negative. That's because this is a positive class training instance. On the other hand, in the case of the hinge loss, you incur a loss for any value of the dot product of Wx which is less than 1. So the idea really here is that you are incurring a cost not only for misclassified instances but also for instances that are uncomfortably close to the decision boundary. That is the notion of the margin which is popularly used in SVMs, and that is really the only difference between the perceptron and the linear support vector machine. So what about the kernel support vector machine? You must have been wondering, well, support vector machines are mostly used in the context of kernels. Can we somehow represent a kernel support vector machine as a neural architecture? Well, the answer to that is yes, except that it's a very special type of architecture which we have not yet discussed, and we will discuss in a later lecture. That special type of architecture is referred to as a radial basis function network. Now, this is typically contains only one hidden layer. And I won't get into the details of this architecture here, but the idea really here is that this hidden layer really performs unsupervised feature engineering with the use of a radial basis function. So, and what you get by using this architecture, a special case of this architecture can be shown to be identical to the support vector machine. But of course, this architecture has become kind of archaic and it is not used too much in the modern era. One of the reasons is that basically most of the deep learning models, they are typically used in cases where supervised feature engineering is needed. Supervised feature engineering works well when the data has very rich structure but it doesn't have a lot of noise. In that case, supervised feature engineering does not overfit your data set. On the other hand, unsupervised feature engineering, like what you use in your RBF network or a kernel SVM, is good for noisy data. So one important aspect which we will go through in many of the later lectures, because we are going to go through many classical machine learning models in subsequent lectures one by one, and we will show how they are connected to very shallow neural models. And what we will show is that by making minor changes to the architecture of the perceptron, we can get all of these classical machine learning models. So for example, if you take your perceptron, you use a linear activation in your output node, but you choose your loss function carefully, you can get many of these models. So you can get linear regression, you can get Fisher discriminant, you can get Widrow-Hoff learning. And of course, we already saw in the previous slide that you get an SVM if you choose a proper loss function, which is your hinge loss. Similarly, logistic regression, again, if you pick a sigmoid activation in the output node and you pair it with a log loss, okay, that is the main difference between the logistic regression and the perceptron. You can also get multinomial logistic regression, which is used in cases where you have k classes instead of binary classes. So in this case, you will use a softmax activation in the final layer with multiple output nodes. And similarly, singular value decomposition, you can represent it as a special type of neural architecture called an autoencoder with linear activation. Now, I haven't yet discussed what an autoencoder is, and we will go through it in later lectures. Similarly, even recommender system, much of the recommender system that you might have seen, for example, matrix factorization for incomplete data, you can use an autoencoder like architecture. It's not exactly an autoencoder, but it's an autoencoder like architecture which has a single hidden layer. And in fact, a variation of one of these architectures is used in a very popular feature engineering method called word2vec. Again, we will go through all of these connections between machine learning and shallow neural network in later lectures, in the subsequent lectures. So one question that arises, why do we care about all these connections? One of these reasons that we care about all these connections is because these connections tell us about the cases where it makes sense to use conventional machine learning. In general, if you have less data with a lot of noise, you want to use conventional machine learning. On the other hand, if you have a lot of data with rich structure, you typically want to use neural networks. And typically when you use very deep architecture with many layers, the rich structure in the data is learned by these deep networks. And in fact, many of these deep networks, what you will do is that they are not fully connected. In fact, the connections are sparse and they are carefully chosen with domain-specific insights. And in these cases, it is possible for neural networks to learn very intricate structure in the data. And the classic example of this is convolutional neural networks, in which they can classify image data with accuracy which now beats human performance.